Good morning, everyone, and welcome to the first session of the day. Today, we have the pleasure to have the Professor Hélène Perrin, who is currently director of the French National Center for Scientific Research and deputy director of the Laser Physics Laboratory at Paris 13 University in France. So just to give you a brief introduction about Professor Hélène. She did his master and PhD in the École Normale Supérieure in the group of the Professor Chloe Tanouji, working with cooling cesium atoms in optical traps. After that, she became quickly researcher of the CNRS and the LPL at Paris 13. And after a few years, she became the leader of the BC group at the university. Professor Hélène has made huge contributions in trapping and manipulating atoms with adiabatic potentials and many other contributions in the area. So Professor Hélène, and thank you for accepting our invitation to the school, and you have the word. Thank you.
Thank you very much, Emmanuel. I'm very happy to have made it and to be with you, even if remotely at the school. I would have loved to come, but I had to cancel at the last minute. So my course will be divided in 3 lectures, one today, one tomorrow, and the next one in 2 days. And the main topic is about superfluid dynamics of Bose-Einstein condensates, of quantum gases, Bose gases, and especially in specific traps that we will discuss tomorrow. So the lecture of today will be the introduction with the basics of BECs, and we will go to next steps in the coming days. Today we will discuss a quick reminder on Bose-Einstein condensation, why it happens, what's happening when we add interactions between particles, and the occurrence of superfluidity, and what is superfluidity and what it is characterized by. And I will, if I have time, discuss collective modes, and in particular one collective mode. And in the second lecture tomorrow, I will describe you a very nice tool that we have developed in the lab, which is the way of trapping atoms with adiabatic potentials. And the geometry I will discuss a bit more will be a bubble trap. And in the third lecture, I will discuss experiments that we have done in my group, where we look at superfluid dynamics of a Bose gas confined at the bottom of this bubble trap. So let's start with this first lecture that I have looked at your program. I have seen that maybe for most of you it will be reminders, but it's always good to be recalled some basics on Bose-Einstein condensation and superfluidity to be more clear in the rest of the lecture. So first, why would we concentrate on quantum gases for the study of superfluidity? Because superfluidity occurred in different systems initially, and in particular in superfluid helium. And the reason why there is a great interest of using quantum gases for the study of superfluid dynamics is that these gases, they benefit from a high degree of control of both their external and internal degrees of freedom. So what we can first state is that the temperature of these gases, of course, is very low, and it can be controlled, and the range of temperature that is available in the lab is between one, maybe not one, but a few nano-K, 5, 10 nano-Ks, up to in temperatures in the micro-Kelvin range. Second, in some cases, you can tune the interaction between the particles. And I will show you an example where people have removed completely the interactions to get access to the non-interacting picture of Bose-Einstein condensation. Then you can play with the geometry in which the atoms are confined. So for example, you can tailor periodic potentials with optical lattices and mimic the motion of electrons in the lattice of a crystal, sorry, with the neutral atoms moving in optical lattices. You can also realize ring traps, and I think there is a lecture series, or at least one lecture by Bill Phillips about ring traps in your program. So this is made possible with the facility of manipulating quantum gases. And you can also access low-dimensional systems with quantum gases by compressing strongly either one dimension of the gas or two of them to realize flat gases, 2D systems, or elongated gases mimicking one-dimensional systems, and access to very different physics when you confine very strongly one or two dimensions. In addition, gases, they can present several internal states, and you can also play with bosons and fermions by changing the species and probe not only, for example, the transport properties of fermions like electrons in a lattice, but also bosons. And finally, quantum gases, they are really easily detectable with resonant lasers, with either absorption imaging or fluorescence. And in this example, atoms are detected one by one, so each little pixel is one atom. And this can allow you to reconstruct the atomic density particle per particle in some cases. So for all these reasons, quantum gases represent a quite ideal system for the study of quantum properties, and in particular for what is the interest of this course, superfluid dynamics. So I give you a few references for the lecture of today, the first lecture. I will base this lecture on the review of modern physics paper of Dalfovo, Giorgini, Pitayevsky, and Stringari that appeared after the Varina School in '98. You can also look at books, in particular the book of Pettick and Smith and the two books of Pitayevsky and Stringari, both the one on Bose-Einstein condensation and the one on condensation and superfluidity. So I recommend them. They are excellent books for your reference if you work in the field. All right, so this is a quick outline of the lecture of today. I will recall what is Bose-Einstein condensation for a non-interacting Bose gas. Then we will introduce interactions. This will lead us to the Gross-Pitayevsky equation. And if we look at this equation in a time-dependent way, we will see that modes appear in the energy spectrum of this equation gives you access to the fact that the gas, when there are weak interactions, is expected to be superfluid. Then I will show you a couple of experimental results in this direction. So very briefly, what is Bose-Einstein condensation and when does it appear? Basically, Bose-Einstein condensation relies on the statistics, and it corresponds to a saturation of the number of particles in excited states. If you have a system with single particle states, which are increasing with increasing energy, above some threshold, the population in the various states is much less than 1 on average. But when you reduce the temperature, then the population of the lower state will increase. And at some point, you will have a number of atoms that can be accepted in the excited stage, which is less than the number of atoms you have, and all the atoms, well, a significant fraction of the atoms will accumulate in the ground state. So the fact that there is some critical atom number given the temperature above which all the supplemental atoms accumulate in the ground state is linked to the statistics, the Bose statistics that the Bose gas obeys. So given a energy distribution E, the Bose-Einstein distribution tells you what fraction of population you can put in each state of energy E. And so in this formula, beta is 1 over kBT. And what is important in this Bose-Einstein distribution is this minus sign here. So if you have E minus mu, essentially, which is close to 0, then the exponential is close to 1. And you see that this denominator will diverge. So you can allow a lot of particles in the ground state where the Bose-Einstein distribution can diverge. In excited states, it is bounded. So by which quantity is it bounded? So each energy, the energy of the one particle states being labeled by EI, the chemical potential corresponding to the gas has to be less than each of these energies. Otherwise, you would have a negative value for the occupation of a state EI. So this has to be positive, which implies that mu is less than EI for all the states, and in particular for the ground states. So now you can use the fact that the chemical potential is less than the energy of the ground state to give an upper bound for the occupation of a state EI. So this occupation of the state is less than the occupation you would get if you replace the chemical potential by the ground state energy. But once you have done that, you get a formula for all the population in all the excited state, which does not depend on the chemical potential anymore, just on the temperature. So you can compute a maximum possible atom number that you can put in the excited state. And so if this maximum atom number is finite, so if this infinite sum converges, then you would have Bose-Einstein condensation if you try to put more atoms than this maximum. So this gives you a critical particle number at a given temperature for Bose-Einstein condensation to occur and have a macroscopic population in the ground state. Or equivalently, if you work at fixed particle number, a critical temperature, which is defined by the temperature at which this critical number is just equal to your particle number. So any supplemental atom has to go to the ground state, or if T is less than Tc, then you need to have a macroscopic fraction of the atoms in the ground state. So the fact that the sum converges or not depends on the density of state. So it depends on the geometry of your gas, on the fact that it is trapped or not, on its dimension. And the sum that we had before can be approximated by an integral where you incorporate the density of state, and a very easy density of state, very easy to compute, and also very common for different situations, is a power law density of state. So if you have a power law density of state with some power k, then you can compute explicitly this critical atom number corresponding to the maximum number in the excited state. And you will find that this number converges indeed as soon as this power of the power law is strictly positive. And so it will give us a Bose-Einstein condensation if k is positive. And in this case, the fraction of particles that you can have in the ground state is related to the temperature and the critical temperature by some power law behavior, where the power law of the density of state appears here. So it's 1 minus T over Tc to the power k plus 1 if the density of states behaves like the power k. So now if we look at some examples, let's start with the Bose-Einstein condensation in a harmonic trap. So in a harmonic trap in dimension d, the density of state is indeed a power law with a power which is d minus 1. So it means if we want that the power is strictly positive, we need that the dimension is strictly larger than 1. So it means that for a dimension 2 or 3 in a harmonic trap, Bose-Einstein condensation occurs. And this, by the way, has been studied by Van der Leyen in the 80s. So this is an example for the first realization of a Bose-Einstein condensate in 1995. This was done in a 3D harmonic trap. And in this case, you can relate the critical temperature to the average trapping frequency in the trap. And the fact that it's really a quantum phenomenon linked to the statistics and not a trivial phenomenon like you have the temperature less than the splitting between states. So of course the ground state is populated, is clear here because the critical temperature is not on the order of h bar omega, the splitting between states, but on the order of h bar omega times the atom number to the power 1/3. So if you have like 1 million atoms, it is 100 times larger than the splitting between states. So it's much larger than the splitting between states. So it's really a statistical phenomenon and not just a thermic phenomenon. So with the 3D case, you expect a fraction in the ground state scaling like 1 minus T over Tc to the power 3. And this indeed has been observed just after the first BEC in 96. So it also works in 2D in a harmonic trap. Now in a box, then in a box, the density of state is also a power law, but with a power d divided by 2 minus 1. So if you want this to be strictly larger than 0, then d should be strictly larger than 2. So only in 3 dimensions can we have Bose-Einstein condensation in a box in a uniform gas. And so the criterion in this case can be recast under the form atomic density times de Broglie wavelength to the cube is larger than 2.6, where the de Broglie thermal wavelength is the ratio between h and square root of mkt with T the temperature. So it's case, the critical atom number scales like the temperature to the power 3/2. So this has been observed a few years after because it's less trivial to realize a box with cold atoms than a harmonic potential. So this is an experiment in the group of Zoran Hatzipabish in Cambridge. And you can observe here the density in the center when you cool down the sample being much larger at the threshold after a time of flight. So this is a condensation in the momentum space. The number of atoms with low momentum is very large in the center. And what is very nice in this experiment is that they were able to show really directly the saturation of the excited states. So if you look at the number of particles in the excited states compared to the number of particles in the condensate, when you increase the atom number, you see that at some point you reach the maximum number of atoms you can put in the excited states. So the number of thermal atoms stays sticked here, while the number of atoms in the condensate increases because of this phenomenon of saturation of the number of atoms you can put in the excited states. Okay, so the usual interpretation in this situation in that if you have a temperature which is less than the critical temperature in 3D. The thermal double wavelength represents more or less the volume or the size of the wave function of each atom, and BEC occurs when this size is comparable to the distance between particles, and their statistics is meaningful, and you have to take into account that you have bosons, and you get a BEC when you have a density larger than this critical density or a temperature less than the critical temperature. So in this case, what is predicted is that you have a single wave function for all these non-interacting particles. All the particles are in the same state. They are described by exactly the same single particle wave function. So all what I have said here was for non-interacting particles. The computation of the critical temperature, everything was for non-interacting particles. But in real life, there are interactions between the particles. So we may wonder if this description still holds. Some tests that has been done very quickly is to check this single particle, this single wave function approach. So is it true that there is a common phase for all the atoms? Is it true that you can describe them as a single wave function? And the early experiments typically were interfering two BECs and observe very nice fringes, like in this experiment done at MIT, or this one done in Munich, where again, you take two pieces of the condensate that you let fall in gravity, and you see really clearly nice interference fringes, which are the signature of the fact that your sample, in fact, is fully coherent and can indeed be described by a single wave function. And this is absolutely not evident, because if you look at the many-body Hamiltonian, you have to take into account with this n-particle system, you indeed have a sum of single particle Hamiltonian, but now you also have the interaction between particles. So the ground state of this big Hamiltonian is correlated in principle, and it should not have just a ground state, which is n times the same wave function in principle. However, we can see experimentally that the single wave function approach works very well. So the idea is that while we stay in the weak interaction limit with dilute gases, which is the case in most experiments, then a mean field description is appropriate, and we will describe indeed the weakly interacting condensate as a single wave function. So what are the properties of this single wave function? We can derive that by starting from the Hamiltonian and assuming weak interactions and trying to find a solution imposing that all the atoms will be indeed in the very same single particle wave function. So instead of looking really for the ground state of the Hamiltonian, we look for a ground state under the form of a product of single particle states with all the same wave function. And we will minimize the energy to find which wave function is more appropriate. So it is a variational approach. We will minimize the energy given this, this form for the n particle wave function to find the best single particle wave function that gives us the minimum energy. And if we do that, we end up for this single particle wave function with the Gross-Pitaevsky equation, which is an equation which is quite intuitive finally, because it consists of three terms. Essentially, it has a form of a functional applied to our wave function equal to a mu psi, where this functional is the Laplacian, which corresponds to the kinetic energy, an external potential, if any, corresponding to the potential energy. And what is new is this nonlinear term where psi appears. And this corresponds to the mean field interaction of the test particle with all the other n-1 particles. And so this is a eigen problem where now this mu appearing here is the chemical potential of our n particle wave function. So in this equation, the interaction term has a prefactor G, which is a coupling constant, the interaction coupling constant, and which is related to a parameter describing the collisions between particles, little a, which is a length, and which is called the scattering length. And this is a scattering length that in some cases you can tune in condensate. Okay, so in all the rest, I will assume here that we have repulsive interaction, so G is positive, and so it will cost energy to add a particle. So given this shape, this Gross-Pitevsky equation, this will lead us to the fact that we will have superfluidity in the system. So just to give you some hint of what interactions do, if you solve the Schrödinger equation in a box, you normally have a sign, the part of a sign. Once you add some interactions, this will broaden the distribution because the atoms will repel each other. And so instead of a sign, you will have something which is more flat in the center with some average density. And the size over which the wave function is bent is called the healing length, psi, and is linked to the chemical potential or to the interaction energy if you prefer. So this psi here is a typical length over which you recover from a zero of density to the average density. And if you go to stronger interactions or more particles, you end up with some fluid which is almost flat and the healing length which is very small. In a harmonic trap, it is more or less the same story. If you have non-interaction particle in a harmonic trap, the solution is a Gaussian, so this shape here. And if you increase the interactions, then it will broaden the Gaussian, and the more particles you add, and the more broaden it is. And at some point, if the atom number is large enough, you go in what is called the Thomas Fermi regime, and now the solution is instead a parabola, which is essentially the mirror image of the potential you had initially. So the Thomas Fermi radius, which is a radius of this parabola, is linked again to the interaction, so to the chemical potential. Okay, so we have seen the solutions in a box and in a harmonic trap. And now let's go to the situation where we place our gas out of equilibrium, which is what is the goal of this course, to look for the dynamics of the both gas. And so if we go out of equilibrium, our Gross-Pitevsky equation we had before with mu psi instead is described by a time-dependent Gross-Pitevsky equation, just like the Schrödinger equation was E psi, and with time-dependent it is minus I h bar d over dt psi. In the same way, the time-dependent Gross-Pitevsky equation reads in this way. So it's just like a Schrödinger equation with this nonlinear interacting term in addition. And in fact, this nonlinear Gross-Pitevsky equation, we can recast under hydrodynamic equations if we make this Madelung transformation, where the wave function we write as some density. So of course, the density is a modulus square of the wave function. So the wave function is like square root of this density times a phase. And so if we replace the wave function in this equation by square root of n exponential I theta, and we separate imaginary part and real part just to have only real equations, we get two equations for the density and velocity and the fluid velocity v, which is related to the gradient of this phase theta. One of these equations is equivalent to a continuity equation. You see that it's a conservation of the mass. And the other equation is really analogous to the Euler equation of a fluid. with kinetic energy, external potential, this term being equivalent to some pressure. And in addition, there is this term which is called the quantum pressure, which is linked to the fact that when you bend the wave function, you have to pay some energy. So related again to the healing length psi. And a very important remark we can make immediately by identifying the V, the velocity of the fluid with the gradient of theta, is that the flow of our fluid is irrotational because the velocity is a gradient, so its rotational is 0. So we are with an irrotational flow, and this will have consequences on how the fluid can be set into rotation. As it is, okay, so these hydrodynamics equations, they can describe very accurately the expansion of the condensate in a time of flight, the fact that when you switch off any trap, the gas will inflate, and in fact, its density after inflation will mimic very accurately what it was before. So you can use this technique to see what was the density in the gas before. The hydrodynamic equations also describe the collective modes. I will come back to that. And more generally, they describe the excitations of the fluid. And I will come back to the phonons in particular. And the fact that the fluid is irrotational means that when you try to set the gas into rotation, you cannot do it unless you create some localized defects, which are called vortices, which are quantized in the fact that the circulation of the velocity around each vortex is an integer times the circulation quantum h over m, where h is a Planck constant and m is the atomic mass. So the fact that this vortex lattice develops when we try to set the gas into rotation is one of the signatures of superfluidity. So I say that from this hydrodynamics equation, we can infer the spectrum of the excitations. So for to keep things simple, we consider the hydrodynamics equation with no external potential. So a homogeneous gas in a box. So the question now is what is the small perturbation spectrum above the ground state? So the equilibrium distribution, if we're in a homogeneous gas, it's easy. It's a homogeneous density, so some density, and the solution is a density which is equal to the communal potential divided by the interaction constant. But now we look for small deviations around this ground state solution. So we will write the density as this ground state density plus some perturbation, and we will linearize the hydrodynamic equation, so those two equations, for a small density perturbation delta n and small velocity, because of course at equilibrium v is 0, so having some v is already first order. So if we do that and we keep only first order terms, we have two equations, so one coming from the continuity equation and one from the Euler equation. And we can try to look for plane wave solutions to these coupled equations, where the density would propagate with some k vector and frequency, and same story for the velocity. So if we write delta n and v like that, we get some conditions on the k and on omega. And if we eliminate the velocity, for example, in these coupled equations, we find the spectrum of the energies corresponding to a given k vector. And so this is the spectrum we find for a homogeneous Bose gas with weak interactions. So how is it like? We can concentrate on two limits. If we look at small momenta, the small momentum limit, where we can neglect this k to the 4 term, then at small momenta, we have a spectrum which is linear with the momentum k. So the frequency being linear with momentum is a spectrum of sound waves with a velocity for these sound waves, which is the speed of sound given by square root of the chemical potential divided by the mass. In other words, this speed of sound is linked to the relation chemical potential equals to mc squared. So this is the situation where you look at small momenta for the spectrum. On the other hand, if you go to high momenta, so then that's a k to the fourth term which will dominate, you will have an energy which is close to h bar squared k squared over 2m. And if you keep the next correction, you find that the energy is the energy of free particles on the top of the chemical potential. So you have particle-like excitations flowing above the energy of the condensate. So the limit between weak k, small k and large k is set by, again, this Healing length. So small k, in fact, means a k smaller than the inverse of the Healing length, and large k means k larger than the inverse of the Healing length. So to summarize, this is how the spectrum looks like: linear spectrum at small momenta, and then a parabolic spectrum at large momenta. So in this region, the excitations are sound waves, and they propagate with constant velocity. And in this regime, we start to remove particles from the condensate and have free particles flowing on top of the condensate. So this spectrum has been probed experimentally. This is an experiment done in the group of Nir Davidson in Israel, where they were able to see very nicely this linear and then parabolic behavior for the excitations on top of an elongated BEC along the long direction. Okay, so the fact that we have a linear spectrum at small momenta has an important consequence. It is linked to, again, a signature of superfluidity. And this signature is linked to the existence of a critical velocity for creating excitations, so which is called the Landau criterion. So why is it so? If you have a spectrum dispersion relation, which is so as a function of linear momentum p, so p being h bar k, if it is equal to Cp or larger than Cp, which is the case here, where essentially Cp corresponds to this line, so we have a spectrum which is larger than Cp. What is the consequence? If you try to drag an object in your fluid and wonder if dragging this object will create some excitations or not. To create an excitation in the fluid, you need to fulfill conservation of momentum and conservation of energy. So before creating any excitation, you had your particle with momentum p, with some energy p squared over 2m, on top of your BC with energy 0. After excitation, if you imagine that you have created some excitation in the fluid, this will give you your exciting particle with, or your object with a new momentum p prime, plus an excitation created in the fluid with momentum p star. And so the new energy will be p prime squared over 2m plus the energy associated to this p star. But conservation of momentum implies that this p prime of your object is the former p minus p star. And if you replace in the conservation of energy p prime by this expression, it will follow that the product of p over m times p prime, so the velocity of your object times the momentum of the excited particle that you have created is larger than C times P star. So as a consequence, you cannot create any excitation in the fluid if the dragging velocity of your object is not larger than the critical velocity C being equal to the speed of sound. So it means that the excitation are created only if the velocity is larger of the speed of sound. So a critical velocity for excitations exists. So this is only true if C is non-zero, of course. So if you remember that C is square root of mu over m, and in fact, mu in this gas is G times N0, which is here or here, mu is G times N0. So if there are no interactions, if G is 0, then mu is 0, then C is 0, and then there is no such critical velocity. It's just because you have weak interactions between the particles that superfluidity occurs, okay? So this also has been tested experimentally. So this is an experiment in the group of Jean Dalibard, where they drag some laser, some defect under the form of a focused laser in a fluid, and no excitation is created if the velocity of the laser is small enough. But if the velocity is larger than some critical velocity, then the temperature increases and excitations are created in the fluid. So the fact that there is here such a threshold is a proof that the Landau criterion works, and that the fluid here is a superfluid. So as I said quickly before, another signature is the existence of vortices. So the rotational of the velocity of the fluid velocity is 0 because the velocity is a gradient of the phase, unless at positions where the density vanishes. So around a point of 0 density, the wave function has a form exponential IL theta, where theta is the azimuthal angle, and L is some integer, just to have the wave function being equal to itself after a loop. And so this means that the velocity field around such a defect, such a vortex, is larger at smaller distance. So scales like 1 over r, 1 over the distance. So you have very large speeds close to this dip of density, and then the speed decreases when you go away. And the circulation of this velocity, if you compute the integral of this velocity around a given loop, so at some distance r, the r in the denominator and the r of the integral, they cancel each other, and you are left with a circulation, which is an integer number times h over m. And so this is called a quantized vortex, and it has a quantized circulation. So the size of this little hole in the center is again linked to the healing length, because just at the border, the velocity corresponds to the critical velocity, which is the speed of sound. And so here, when 1 over xi, h bar over m xi is equal to the speed of sound, you are above the critical velocity, and the density has to vanish in the center. Instead of having, in principle, you could have multiply charged vortices, but they are unstable. And so if you rotate a gas very quickly, what happens is that instead of having a single vortex bigger and bigger in the center, in fact, you have many vortices that are spread all around the gas, each of them being singly quantized. And so these vortices arrange in the triangular lattice. You can see here that the lattice formed by these vortices is triangular, and this is called an Abrikosov lattice. So this is a second signature of superfluidity, the existence of these vortex lattices. So first one was a critical velocity, and the second is this one. And the third one I would like to mention is the existence of collective modes. Once you consider not only a uniform gas, but also a gas confined in a harmonic trap. So this time, I will keep the external potential under the form of a harmonic trap with trapping frequency omega. And I will apply the same approach as before, trying to look at small perturbations on top of the ground state. So if I do that, and in addition, I neglect the quantum pressure, which is relevant when we are with the densities large enough, so in the Thomas-Remy regime. And I linearize around the ground state solution, then I can find an equation on the perturbations delta n on top of this density. And by solving this equation, I can again find the spectrum of excitations, so the energy of the eigenmodes. And so these energies for a three-dimensional spherical BEC can be expressed with quantum numbers, radial quantum number n and orbital quantum number L, and the projection of this angular momentum on the z-axis, which does not contribute to the frequency, but describe the shape of the perturbation itself. So we expect this kind of a spectrum for the excitation of a BEC in a trap 3D, in a three-dimensional trap. If instead we are in a 2D trap, so with a 2D gas confined in a two-dimensional trap, instead of the 3, I have a 2 here, but the idea is more or less the same. And so these little dots here correspond to these eigenenergies of these eigenmodes of the trap condensate. Each line corresponds to a given n, and then when I increase n, I have n equals to 1, 2, 3, etc. here and there. The critical velocity for a gas confined in a harmonic potential would correspond to exciting surface modes around the surface of the Bose gas. So the little dots I have marked here, blue, red, and green, are the first low energy eigenmodes. And they are really easy to describe. So this red dot here corresponds to frequency equal to the trapping frequency. So it's called the dipole mode, or the center of mass mode, where the whole gas as a whole oscillates in the trap. So this mode is already there for a thermal gas. In fact, it's just the center of mass of the gas oscillating in the harmonic trap. But there are other modes which are not there for a thermal gas. So the monopole mode corresponds to the breathing mode. So when the gas is compressed and decompressed all together, and for a 2D gas, the frequency is twice the trap frequency. It's at 2 omega. And this mode, in fact, can be used to study the equation of state of the gas, because it can probe how much the gas is modified when you increase the pressure or decrease the pressure. When you excite this mode, the pressure is modulated. So thanks to that, it can give you access to the equation of state. And these green spots here correspond either to quadruple mode or scissors mode if you have either an isotropic gas or an anisotropic gas. The quadruple mode and the scissors mode, they are there only if we have a superfluid. So they can be used to probe the superfluid character, just as the critical velocity or the existence of vortices can also be used to probe superfluidity. So the quadrupole mode corresponds to a deformation where the gas is stretched along one axis, compressed along the other, and vice versa, or with a rotating deformation. Whereas the scissors mode corresponds to an oscillation of the main axis of the gas being in an anisotropic trap around this main axis. So like scissors that you open and close. Okay, so I think I will just show you the general probe that we have made of these modes in our experiment and then finish because my time is almost over. We have looked at the first excited modes, so this spectrum in a sense, in a two-dimensional gas produced at the bottom of the bubble that I will present you tomorrow. In an anisotropic situation. So you can imagine that the gas is flat, so it's only two-dimensional, with a harmonic trap with two different frequencies in the directions x and y. And in this case, you expect to have two dipole modes with different frequencies omega x, omega y, and something which is closer to a quadrupole mode and a scissors mode. And indeed, when you compute numerically the modes you expect for their frequencies, that's this graph here, and for their shapes in terms of mode, that this graph here, here you have to, this is the average distribution, and you have to interpret these data as the picture you will get at some time in the evolution is the average multiply by one of these densities. So this is minus, this is plus. So here, for example, it's the oscillation along this direction, because if you have less atom here and more atom there, it corresponds to a gas that is shifted downwards. So this mode is an oscillation along this axis. So it's one of the dipoles. This one is along this axis. This one is elongated along this one and shrinked along that one. So it's like a quadrupole mode. And this is the scissors mode, where, for example, the gas is more oriented to the left, and next time it will be more oriented to the right, etc., and higher order modes. And this one is more the monopole, where the gas expands and is compressed. So to probe this experimentally, what we have done is to prepare a 2D gas and excite it in all different manners, like shrink in all possible directions, and record many absorption images of the gas moving, shrinking, being excited in all ways. And then the idea is to make a general statistical analysis of the results with what is called a principal component analysis. And this principal component analysis consists in computing the average picture and also computing then the correlations between all the pixels and diagonalize the correlation matrix. And so if you do that directly from the pictures without any knowledge of the gas, you can extract the main motions that are present in the movie. And what you find indeed is that you recover the dipole mode along X, the dipole mode along Y, some modes which is more like a monopole-like mode, and the famous scissors mode I have mentioned, which is a signature of superfluidity. So already by just looking at how the gas is moving, you can say, okay, this guy here is indeed a superfluid, and it moves as it should. The scissors mode is present, and we can check superfluidity. So in fact, in our group, we have studied in more detail the monopole mode to probe the equation of state, the scissors mode to probe superfluidity. So I won't have time finally to give you more insight on the superfluidity. So the idea is to determine in which regime we are. Is a superfluid, the scissors mode present, and then it is a superfluid, or is it not present and then it is a classical gas? So I will skip this part. But the result is that indeed we are able with this analysis to put a threshold between superfluid and thermal by just dynamical means of looking how this scissors mode is present. And so I directly go to my summary. I have shown you that Bose-Einstein condensation occurs below some critical temperature. This is true in a 3D box, not in a 2D or 1D box. And this is true in a harmonic trap as soon as we are at least in 2 dimensions, not in 1D. I have shown you that we can describe the dynamics of the condensate in the mean field regime using the Gauss-Pitaevsky equation, or equivalently the set of 2 hydrodynamics equations. And then I've shown you that a weakly interacting BEC is a superfluid with different characteristics that we can use to prove this superfluidity: the existence of a critical velocity, the existence of vortices, and the presence of some specific collective modes like the scissors mode or the quadruple mode. Okay, so next lecture will be devoted to the way we perform some specific trapping potentials using adiabatic potentials, and that we will use then to study superfluid dynamics of ABEC inside this potential. So thanks for your attention, and I'm ready to answer if you have a couple of questions.
Professor, thank you for the very nice talk. And actually, we have a part of the audience here in the auditorium, and we have another looking us on YouTube. So we are open for questions here.
So, hi.
Hello?
You mentioned that in a box, you cannot have a non-interacting BEC in 3 dimensions, but in an harmonical trap, you can have it in 2 dimensions. So is there some intuitive way to see why this happens? Is this an advantage of the harmonical trap, that you can have a 2D trap, 2D condensate, or a disadvantage of the box, of the square trap? Or, I mean, are there other traps that allow 2D condensates?
Yeah. The key point is the way the density of state depends on the energy. So this law, yes, oops, it was here. This scaling is critical. So the point is that if you have many states at low energy, you will have a hard time to have a BEC. And the reason why is that the BEC is saturation of the excited states. But now if you have a lot of states at low energy, it will be very difficult to not populate them. And this is what happens with 1D gases, for example. With 1D gases, in a box, for example, the scaling is like energy to the power -1/2. So it's diverging the density of state at low energy. And so as you have so many states available at low energy, you have no chance to populate only the ground state. And for the case of a harmonic trap, it is a critical dimension. If you take d equals to 1, then you have no dependence of the density of state with energy. Of course, we know that in a 1D harmonic trap, the states are evenly distributed. They do not depend on the energy. And again, it's a critical dimension in the sense that you have logs everywhere. And so you have a divergence but it's just a log divergence. So you will recover some condensate in a finite system, typically. But if you go to the thermodynamic limit with infinite size systems, then that's where you will lose condensation. So there are experiments in elongated gases. As they are finite systems at very low temperature, they recover some BEC, but it's with temperatures much less than what you would expect in 2D or 3D, which corresponds to the degeneracy temperature. So for each system, you have to wonder if the density of states at low energy is limited or kind of diverges.
Okay, thank you.
More questions?
Hi. So I was wondering, like, if I understood correctly, you were only considering the mean field terms, right? What happens if you go like beyond mean field terms in the Gross-Pitevsky equation? Like, when is it relevant to consider those terms?
Yeah, so this is relevant as soon as you leave the dilute regime. So I don't know if I have written the dilute condition, maybe not. So I said it's relevant for a dilute gas. So the dilute condition is stated by the density times the cube of the scattering length being much less than 1. In fact, you can go further and say, okay, what is the first correction to my Gross-Pitevsky equation? And so you can introduce a Bogolyubov theory with the eigenmodes of Bogolyubov. And what you find is that the corrections case like square root of density times a cube. So this is relevant if square root of density times a cube is much smaller than 1. And if not, then you really have to take into account the correlations between particles. And this is very much true, for example, if you go to a lattice. In optical lattices, then you enhance, in fact, correlations between particles by having these sites that are set already in your problem. And the correct description of your problem is more the Bose-Hubbard Hamiltonian than the Gross-Pitevsky equation, especially in the limit where the interactions become larger. So this limit corresponds really to the weakly interaction regime, and beyond mean field correction appear once you increase the interactions. And the first corrections, they appear under sums with square root of NA cube and further corrections. So there are corrections that you can compute. And for simplicity, I did not enter into that, but yes, at some point, you have to take into account beyond mean field corrections.
All right, thanks.
You're welcome.
Dalila?
Hello, Hélène. Thank you
Hello.
for the nice talk. I have 2 questions. So I would like to know, how do you excite the breathing modes without creating a perforation oscillation depending on the perturbation that you do? And also, I would like to know, how do you extract the breathing modes from the exertion images, since everything looks the same? Just that.
Yeah, so I don't know if I will spend time in the lectures on the breathing mode in detail, because I did that 3 years ago, but probably I will change. This will be my 3rd lecture, but I think I will change it. So probably I will not come back to that, so I answer now. But if you're interested, I can give you more material. To excite the breathing mode, what we do essentially is to suddenly change the trapping frequency everywhere. So if, for example, I open the trap a little bit, now the shape of the gas is not at equilibrium anymore, and it will expand and then oscillate around the new equilibrium size. In fact, we did it in two ways, either doing that or instead of changing abruptly to oscillate slightly the trapping frequency. So trying to excite it resonantly. So the two are possible. And the way now we observe is to switch off everything, make a time of flight, and measure the size of the cloud after time of flight. And if it oscillates, then we will see it also on the velocity distribution. In the velocity field in this mode also oscillates. And so we make the imaging after time of flight because the sensitivity is larger than if we try to image in situ where the amplitude of oscillation is too small. So the observation is done after time of flight.
Thank you.
You're welcome.
So I think that we have time for one more question, and before to go to the YouTube questions.
Helen, my name is
Hi.
Bruno. When you mentioned that you use principal component analysis on the images to characterize the collective modes, I was wondering if is there a group of images that are analyzed, or is a video that you analyze, or only a picture and you can capture the collective modes, and if there are machine learning techniques that could be applied to that too. And
yes, good question. So first, let me point that if you are interested on the New Journal of Physics website where this paper has appeared, there is a video abstract where Romain Dubecy explains how it works, and it like 5 minutes video or 4 minutes, where you have the flavor of it. The idea is to take all the 133 pictures as pictures and to compute the correlations between the pictures. So you will compute the correlation of this pixel, well, or yes, more or less this pixel with this pixel for the whole sample of 133 pictures. And so you build a correlation matrix with all the coordinates of 2 pixels, and then you diagonalize this correlation matrix, and this is what gives you these principal components. And we limit ourselves to the more important components, the one who have a larger eigenvalue, and then we cut, otherwise it would be much too large. And after some point, because of the noise in the experiment, the next components are less meaningful. It's just noisy pictures. That's, by the way, that's also a way you can use to filter your pictures by doing PCA and removing all components larger than the number 10, for example, because they are not relevant. And people also use this approach to filter pictures. So at the time, we were not using machine learning, so I'm not sure if it can be applied, but probably yes. I mean, it's like an overall analysis of all a big set of pictures. And this is one of the way, it's a kind of machine learning, if you like, but it's done with usual statistical tools.
thank you.
Well, you're welcome.
Okay, so we have one question on our audience in YouTube. So how is the dynamic of the Gross-Pitayevsky equation different from that the Euler equation?
Well, the only difference is quantum pressure. And it is relevant as soon as you have a small object, a small size thing like a vortex or the border of the condensate in a box, because this term is large when the distance is small. It is a Laplacian. So the typical, this term will be the same order of magnitude as this one on a scale of psi, again, the Healing length. So this term is relevant if you try to describe a vortex lattice. You really need it. But if you look at collective modes where it's an overall big shape, This term will be important only at the very end where the density is close to 0, and then you have a correction with respect to the inverted parabola. So if you look at this description, for example, the inverted parabola is a magenta line, and it fits really nicely the atomic distribution. Just on the very side here, the kinetic term is important and not negligible. And that's where also this correction term up here will be a non-zero. So that's the main difference with Euler equation.
Okay, thanks. So let's thank the Professor Hélène again, and thank you so much.
You're welcome.
Okay, thank you, Professor. We will see you soon.
So our next lecture is Professor Ubirajara van Kolck. Bira, it's a pleasure to have him here. Bira has a position at CNRS in France, in Marseille, and also he's a professor of physics at University of Arizona in the US. He received an undergraduate degree in physics from University of São Paulo, and a master's from IFT also in São Paulo. Then he went on to get his PhD from the University of Texas at Austin under the supervision of Steven Weinberg. Then he held postdoctoral and research faculty positions at University of Washington and Caltech. He has several fellowships, appointments, and prizes. I just want to highlight that he was the recipient of the 2020 Hermann Feshbach Prize in Theoretical Nuclear Physics. And the citation for this prize reads, "For pioneering contributions to effective field theories of nuclear systems which have transformed low-energy nuclear theory." His research interests center on effective field theories for nuclear and atomic systems, and on the emergence of nuclear structure from the Standard Model and its extensions. So I do have a warning for the audience. Bira likes to interact with the students, and if you don't ask questions, he's going to poke you until you do. So thank you very much, Bira.
And if we ask questions, o microfone não, tá? Tá. Obrigado, Lucas, pela. Oh, sorry. Thanks, Lucas, for the introduction. Thanks for the organizers for the invitation. I left Brazil something like 35 years ago. The country has changed quite a bit, and one of the things that I noticed that's very nice here in this school is how much the students ask questions. When I was a student, Brazilian students would never ask a question. So I hope that you continue to ask questions, in particular to me. I even take questions in Portuguese. Huh? I'll try. Or Spanish and English even. Yeah. I have 3 lectures, and I would like to talk to have a slightly different approach than many of the other speakers. My interest is not so much in particular phenomena that I will then treat with the different theories, but it's the opposite. I have a theory, and I see what phenomena come out of it. And normally I'm not interested in particular in cold atoms or even in atomic physics. My main area is nuclear physics. But I use a framework, a theoretical framework, that is broad enough to include atomic physics. So I'm going to talk about this framework, effective field theory, and emphasize the applications to atomic physics, but not only. So effective field theory is a framework to incorporate the idea of universality. So I'm going to explain a little bit what that is, and then introduce effective field theory, and then go in some detail over the two-body system. So this is supposed to be a lecture, not a seminar. Of course, as I go on, it becomes more and more seminar-like because there are lots to cover. But so I hopefully I end the first lecture around here, around the end of the two-body system, and then address in the next lectures some general ideas about field-body systems, and then apply them to two-component fermions, bosons, and four-component fermions, a particular type, nucleons, which are realized in nuclear physics. I gave some similar but not identical lectures in Les Houches a couple of years ago, so in case one wants to see some write-up, that's a reference. So, okay, universality, I'm going to start with the very well-known features of universality in many-body systems, in condensed matter systems, and everybody probably has seen this before. If you have a substance that can have a liquid-gas phase transition, then you know that this transition line, where is the cursor, ends at a critical point. Beyond the critical point, the transition is between liquid and gas is very gradual. Along the transition line, there is a difference in the density of the liquid and the gas phases. And as you approach the critical point, this differences in density go to zero, and they go to zero in a way that there is a coefficient there in front, which is very dependent on the substance, but the power law that governs this approach has the same exponent regardless of the substance. So it's universal in that sense. Close to the critical point, the physics is dominated by density fluctuations of all possible sizes. In fact, the correlation length diverges, again, with a given exponent that's universal. Similar thing happens for a transition for a ferromagnet with one axis, where you can have magnetization in one direction or magnetization in the other direction. And again, the magnetization goes to zero at the critical point, but according to a coefficient that depends on the substance and an exponent that is independent of the substance and moreover is the same as for what looks like a completely unrelated phenomenon of the liquid-gas transition. So here what we have is spin fluctuations, but we still have a correlation length with the same exponent. So you see that there is something in the physics of the system that is quite independent of what happens at short ranges, at short distances, and affects very different kind of transitions. So we're going to see in these lectures that there is, at the field body level, there is a similar, there's similar phenomena that we are going to see, that nuclear and atomic physics, which are very different in details, behave similarly. And what's essential here will be quantum mechanics. So, you know, in classical mechanics, if you have a potential with a certain size, then you are going to have orbits for the objects which have sizes comparable to the range of the force. But the same is not true in quantum mechanics. In quantum mechanics, we can have systems that have a size that's much larger than the range of the interaction, and that's what's going to be the key for this universality in field body systems. So there are two obvious questions about this. How can this be? How does this arise? And then, and that's what's going to be most of my lecture today. And then we wonder what, in this intrinsically quantum mechanical situation, what are the structures that emerge as I increase the number of particles of the type that have this property of having sizes that are much larger than the ranges of the force, or than the range of the forces. So, as you well know, in quantum mechanics, basically everything is given by the Schrödinger equation. I mean, it's still Hamiltonian, like in classical mechanics, but we have something called a wave function that obeys the Schrödinger equation. The Hamiltonian, I'm going to be general. It can include, of course, it has kinetic terms for every particle. Here, the number of particles I denoted by A. Sorry, I wanted to change this to N to conform to more to atomic physics notation, but I forgot. You can have interactions among the pairs of particles, triplets, and so on. And then the Hamiltonian acting on the wave function is the energy times the wave function, and I'm going to, throughout these lectures, denote the energy by k squared divided by 2 times the reduced mass, mu. Soon I'm going to specialize to particles of the same type, where all the particles have the same mass, but for now I'm going to keep this a bit general. And then there are 2 important properties of the wave function that we are going to invoke often here. First is the uncertainty principle, right? I can Fourier transform the wave function into momentum space, which is what is represented by this equation here. And the uncertainty principle is very important because we see that when in any practical situation we can only access certain energies or equivalent certain momenta, and limited by some scale that I'm calling m high here. And that means that I am only probing distances bigger than the inverse of this scale m high. This is a good point to emphasize that I use a system of units that's not very popular, I think, in atomic physics. But it's standard in particle and nuclear physics, which is to take h bar equals 1 and c equals 1. And an advantage of this system of units is that the units of everything is the same, essentially. Right? The units of mass, energy, momenta, inverse positions, and inverse time, it's all the same. So there is essentially one scale, and you can, if you want to emphasize this role of different scales in the problem, this simplifies life quite a bit. So that's why I'm saying momentum smaller than a mass scale and distances larger than an inverse mass scale. So this is I'm going to take this to heart, this uncertainty principle to heart in my lectures, right? So it's, I cannot assume that I know physics at arbitrarily small distances, because I don't. I have no experimental access to those. So I'm going to have a sort of realistic approach that I'm going to build my theory for the distance scales that I'm interested in, or that I have access to experimentally. No, you have access to experimentally. The other important property of wave function that we'll need is what can be called the statistical principle, that the wave function has a certain behavior under the permutation of two particles, and as you well know, we can have bosons or fermions according to the sign of the wave function under this permutation, and this is going to play a role when we go beyond the two-body system. So this was all very well known for everybody. I don't know how well known it is that essentially the whole information that you have from the Schrödinger equation is also contained in what's called the S matrix. This comes from, well, the idea of the S matrix appeared before, but it was this idea that the S matrix is fundamental is basically due to Heisenberg in 1943. It continued in particle physics for a while as a sort of attempt to describe the whole particle physics in terms of S matrix, the S matrix program. There is a resurgence of this approach in particle physics nowadays. What we are going to see is that the technique that I use, effect field theory, is just a way to produce the S matrix. I'm also going to talk about the T matrix, which is very closely related to the S matrix. So let me take to be concrete, not general, case of two-body elastic scattering. So there's just two particles that come in opposite directions, go out in opposite directions. And let's say two identical particles as well for simplicity. They are going to have the same, there was some energy before, the same energy after scattering, hence the magnitude of momenta are k. So you see that this scattering process is described by two variables, k, essentially the energy, and the scattering angle. So I can take this object, the T matrix, and do a partial wave expansion in terms of Legendre polynomials, and I will concentrate on the partial wave amplitudes. And these partial wave amplitudes can be written in terms of what are called the phase shifts. And the partial wave amplitude is related to the partial wave expansion of the S matrix by this equation here, so that the S matrix is entirely given in terms of this quantity, the phase shift, which is then a function of the energy. There are a couple of properties of the T matrix, or equivalently the S matrix, that I will need in this talk, and we'll come back again and again. First of all, the T matrix can have poles. That's when the inverse of the T matrix is 0. And the poles are basically three types. There can be bound state. So in the complex on-shell momentum plane, so the plane of complex K, we can have a bound state, which is a pole in the positive imaginary momentum axis. I can have a pole on the negative imaginary momentum axis. That's called a virtual state. And I can have a pole that's somewhere off here in the lower half of the complex plane, and that's what's called a resonance. Some people refer to the virtual state as a resonance of zero width. Okay, I'm going to stick to this notation here. And we are going, in this talk, in these lectures, mostly we deal with bound states, so forget about the other ones for now, but everything can be generalized to those. One important limit that I'm going to come back over and over to is the unitarity limit. That's the limit where the S matrix is -1. So if you look at the S matrix here, is the identity. The S matrix then connects the initial and final states. When it's 1, it means that nothing happened. So the T matrix represents the interaction. But when the T matrix is given by this value here, then the S matrix is -1. So it's not 1, so it's not, something is happening, but it's a very specific S matrix that has no scale in the problem. So scale invariance is going to be associated with this unitarity limit. Come back to that. And another property of the inverse T matrix is that for short-range interactions, one can expand, perform an expansion at low energies. That's well known as the effective range expansion due to beta in 49 or maybe even earlier. And it can be written in this form here in the slide, in particular, that apart from a factor here that depends on the angular momentum, it has an expansion which has a constant term, which is the inverse of the scattering length for the S wave. It's called scattering volume for the P wave and so on. An effective range, which is term linear in energy, the shape parameter, term quadratic in energy, and go on. And then there's what's called the unitarity term, which is an odd power of k, and therefore non-analytic in the energy. So this is all very well known from any quantum mechanics text. Let me illustrate the issue that I want to deal with, which is systems that have a size that's much larger than the range of the force. And for that, I'm going to take the simplest possible, I think, toy model, the spherical well, or square well in 3 dimensions, but spherical. There is a very nice paper by a Brazilian physicist, Nussensweig, in 1959, where he dealt with the spherical well and studied all these properties of the T and S matrices. So I'm not going to go in detail how you find the T matrix out of this square well. I'm going to give soon an example of how to find the T matrix in another example. For now, let's not get distracted. Let me assume that you know how to find the T matrix. In particular, in the S wave, that's what you should be able to get this equation here. If you don't know how to do that, just assume that this is true, and we can talk about this a bit later. So the T matrix for the square well is given by that form over there. So I'm writing a square well, right? So this is a theta function. So the radius of the range of the square well, I'm calling R, big R. And the depth of the square well, I'm writing in terms of the reduced mass, the depth, the range of the square well, sorry, and a parameter which is dimensionless, and I'm calling alpha. That's why I define this way, because alpha is dimensionless. It's a bit hard to talk and breathe with this mask. So the square well is, the spherical well is sketched here. And we can take this amplitude here and do that expansion at small energies that I mentioned in the previous slide, the effective range expansion, match it to that, and find formulas for the scattering length, effective range, and other stuff that I'm not going to bother to do. So here are the formulas in this particular example. And what I want to draw your attention to is the fact that if I take an alpha depth without any special prejudice, some number of order 1, you're going to find out that the scattering length that this number here is going to be a number of order 1, but not particularly close to 1, the scattering length is going to be of order r, and same thing for the effective range. So this is a situation that's closer to classical mechanics. So if I plot now, so if I see what I get when I solve the system, so here's my square well, I'm going to find a level, a bound state at some generic binding energy, and I'm going to have a wave function that grows and falls, for the ground state, say, grows and falls. And what we find is that the fall off is given by the scattering length, more or less, and the scattering length has this value of order r, big R. So nothing special happening here. You see that the wave function will be mostly concentrated inside the square well. And this is indeed the typical situation if you make a plot of the probability of getting a certain scattering length when this alpha can have any value with equal probability. You are going to see that the majority, I mean, the probability is really much high around a scattering length of the order r. So nothing special is happening here. However, if I look at a bit more detail at the form of the T matrix, I find that it has zero energy poles at particular values of alpha, which I'm calling alpha C, alpha critical. So at these values of alpha, I mean, if I choose an alpha that's close to these values of alpha, close by meaning that alpha over alpha C is close to 1, then what you find out is that we can approximate this formula here in this fashion. And if alpha is close to, alpha over alpha C is close to 1, you see that the scattering length can be very large. The effective range is still of order r. So we have a situation where the scattering length is much larger than the effective range. So I can say that there is a new scale in the problem corresponding to this new small scale in the problem that I'm going to call Aleph, which is this small number times the inverse of the range of the potential. So now I have a problem with two scales, the range of the potential and some other scale which corresponds to much larger distance scales. The unitarity limit is nothing but the limit where alpha tends to alpha C and the scattering length diverges and the effective range goes to R. So in this situation, what we have is I'm taking the range of the potential to be close to one of these critical values. That means that the energy, there might be a bound state, but this bound state is going to be very close to threshold, and the wave function is going to spread over large distances, characterized by this scattering length. And the unitarity limit to this, when you go towards the unitarity limit, this wave function spreads very far, and therefore we are in this situation where the particle most of the time is going to be outside the range of the potential, which is purely quantum. Now, to get to this situation for, say, if I want A0 over R to be close to 2, for example, you see how the probability of getting that is very, very small. So we refer to this as fine-tuning. So the important lesson of this particular example is that we can have a situation, this intrinsically quantum mechanical situation, as long as we fine-tune the interactions. So what's fine-tuning? This is the advertising world view of fine-tuning. You park your nice Buick Regal in a parking lot in the US during the pandemic. There's not many cars around there, and the satellite from certain country falls on top of your car, and you wonder why always me, right? Always my car. This is a fine tuning, could have fallen anywhere, falls on your car. Now, you guys are very used to this fine tuning situation. I think Vanderlei made a lot of money out of this, right? In the atomic scenario where you can achieve this fine tuning with a magnetic field, the phenomenon of Feshbach resonance, generically you have two channels, and you have a bound state in the closed channel, and you can adjust the relative position of this bound state with a magnetic field. And when this bound state goes to the threshold of the open channel, then the scattering length goes to, that's the unitarity limit where the scattering length goes to infinity in magnitude. So this has been well exploited in atomic physics. I think it's also well known, hopefully, in atomic physics, there are situations where this happens naturally, this fine tuning. And the typical example, which I will return to in these lectures, is helium-4 atoms, which are bosons. So if you have, they are neutral atoms, so if they exchange the two photons, two-photon exchange is allowed. That's the van der Waals interaction. The van der Waals interaction has a typical, well, it's, in one sense, it's a long-range interaction because it doesn't have an exponential fall-off or anything. But it has a 1/6 tail and, well, and then corrections. And then associated with that, there is a dimension full quantity, which in this case is of order 5.4 angstroms on a typical atomic scale, which I can think of as the range of the interaction. And if you extrapolate the results that exist for helium-4, you see that the scattering length is of order 100 angstroms, and as you'd expect, the effector range is of the order of the van der Waals length. So this is exactly the situation that I described before, and it happens naturally. What we don't have is the ability to, without a Feshbach resonance mechanism, to change this, but you see it, we are, in a sense, this is pretty, the ratio between A0 and R0 is pretty large, and in a sense, we are close to the unitarity limit. Surprise, surprise, the same fine-tuned situation, not as fine-tuned perhaps, but it happens also in nuclear physics. So nuclear physics, the basic ingredients are nucleons. Nucleons are, you can think of as 4-component fermions. What's a nucleon? Well, it's either a proton or a neutron, and then the spin is a half for each one of these guys, so can have spin a half in one quantization axis minus a half in the other one, so we have 4 components of fermions. The interaction is totally different from the van der Waals interaction of helium-4. It consists basically, and this is a bit of a lie, but okay, a bit of the simplification, but basically of something called pion exchange. So there is a particle called the pion, which was suggested by Yukawa in 1935, that mediates the nuclear interaction, and you can have 1 pion exchange, 2 pion exchange, and a bunch of other stuff that I'm not going to go into. That's shorter range that depend on the strong interactions among the quarks and gluons that make these particles. The force is totally different because the main component of, one of the main components of this force is what's called a tensor force. It depends on the spins of the particles in this particular fashion here. It has an exponential fall-off according to the mass of this particle, the pion. And then I've put out the nucleon mass here in front is about 940 MeV. And then there is a dimension full quantity that I'm calling RNN. So there, in this case, and then there's more stuff, but there are two scales. There's the inverse of m pi, which is a number 1.4 Fermi, 10 to the minus 15 meters. So we're talking about much, much smaller scales, of course, than atomic. And this RNN happens to be comparable with, a factor 2 is the same number. Now, if you look at the measured scattering lengths and effective ranges, so you have two of these particles' nucleons. The spins can be, as I said, each one can have spin. Each one has spin a half. So the spin can be of the sum can be 1 or 0, right? So there is total spin 0 here. The spin singlet, spin triplet. These quantities have been measured, and you see that the effective ranges are comparable to the inverse pi and mass. But in one channel, the scattering length is negative and very large. That's a reflection of that type of state that I mentioned before, a virtual state. It's a pole in the negative imaginary momentum. And here, clearly, there is a lot of fine-tuning. But there is no bound state per se. It's a virtual state. In the other channel, there is a bound state. It's called the deuteron. It's the simplest nucleus, or simplest non-trivial nucleus, made out of a proton and neutron with spin 1. And you see that the scattering length is not as huge as here, but it's still quite a bit larger than the inverse of the pi and mass. So again, we see a situation where naturally the system is fine-tuned. Now, we have a tentative explanation for what's happening. I'm not going to go into the details, but essentially the fact that the underlying theory for the system, QCD, quantum chromodynamics, has essentially two scales, one corresponding to a number of order 1 GeV that sets most of the masses, and another one which is quark masses. And the quark masses are, let's say, 10 MeV or so, quite a bit smaller. And the pions get their mass from the quark masses. So that's why the pions are light. And in QCD, you can vary the quark mass essentially independently. So that's what's called that's done in what's called lattice QCD. And when you change that quark mass, the scattering length is going to change. So what I plot here is a possible scenario to explain this fine-tuning in this spin 1 channel, also called the 3s1 channel, where the deuteron lies. And one possible scenario is that as you change the quark masses, or equivalently the pion mass, you go through a point where the deuteron goes unbound. So this is not quite the same as the Feshbach mechanism, because we're talking about one channel, but in a sense, the quark masses play a role similar to the magnetic field in a Feshbach resonance. Of course, we can only vary the quark masses in this imaginary world of lattice QCD. But then, if this is correct, then the real world just happens to be close to this magical value where the deuteron goes unbound. So I'm not going to come back to that, but this is active area of research. But it has some similarities with the Feshbach mechanism. So whatever the mechanism is for this fine-tuning, there is a fine-tuning, right? And my attitude here is I'm not going to worry about what causes this fine-tuning. I'm going to accept it, and I'm going to incorporate it in my theoretical description. So how do I do that? Well, first of all, I notice that if my wave function is much larger than the range of the potential, then as long as I get the same scattering length, my wave function will, for most of the region in space, will be the same. It's going to be given by an exponential of proportional to an exponential of minus r over r0. So that means that if I have, for example, a square well that has a much smaller range, but the depth scales appropriately, the wave function outside is essentially going to be the same. So this is the idea of universality, that the form of the potential at short distances doesn't really matter. So here I illustrated with 2 square wells, but it could be something else, and the same idea holds. What matters is A0, and I can forget the relation between A0 and the specific potential that I have before. So I'm going to rewrite that potential in something that looks like a delta function. So I multiply and divide by 1 over r cubed and some numerical factors, because I see that when r is very small, big R is very small, this looks like a delta function. So this is what's called a regularization of a delta function. And I'm going to rewrite my alpha in terms of alpha c in A0. Alpha c is just some constant. And I get my A0 here, and I get the dependence on R. And I'm going to call this whole thing just a parameter, C0, which depends on the specific regulator now. I'm going to see this R as a regulator, something that's arbitrary. I don't really care, because I don't care about the form of the potential at short distances. So I can get the same dynamics from a delta function. So this is just what you learn in classical electrodynamics, right? Multiple expansion. If I'm interested in physics with a very long wavelength, when I have a charge distribution, in the first approximation, that charge distribution I can take to be a point distribution with the total charge there. If I want some more precision, I'm going to consider higher multiples, and it's the same thing I'm going to do here. My starting point is going to be a point interaction, and I'm going to consider corrections. And that's what effect field theory is in this particular case. I'm not going to be content in describing my system by a delta function interaction, which I'm going to represent pictorially as 2 particles coming in and interacting at a point and going away. But I'm going to consider 2 derivatives of delta function and 4 derivatives of delta function and so on in a systematic expansion. The leading term, which is going to be this delta function that I've been talking about, accounts for the scattering length, or equivalently the binding energy of this shallow system. And it's characterized by a momentum that's much smaller than the range of the interaction. And then I have corrections from the effective range that account for some of these properties of the finite range interaction. And I can go on forever. Now, in the case of atomic physics, where I have a van der Waals potential that doesn't have exponential fall-off, this only works up to a certain order here, which is exactly Q squared for the potentials of interest in atomic physics. In nuclear physics, you can keep going on forever. So, but then I'm going to look for a description that systematic starts here with corrections here and go and so on. Now, this is only 2-body. Starting probably in the lecture tomorrow, I'm going to consider more bodies. And we are going to see that, well, there are going to be other elements. When I have bosons, for example, they can get arbitrarily close, and something called the 3-body force is going to be important. It's going to account for a new scale that appears in the 3-body system. What's a 3-body force? A 3-body force is anything that disappears when any one of the 3 bodies is removed. So the simplest example that appeared in Wikipedia for a while and then was removed, perhaps because it was considered too childish, is jealousy, right? If you have 3 people, regardless of gender, and 2 are always together, and the third one might feel jealous, removal of any of the three bodies in the system will remove the jealousy. So jealousy is a three-body effect. More generally, a three-body force is going to be something that it's not reduced to a combination of two-body forces. The reason to pursue this approach, which is, as I said, similar to the multiple expansion, is just its simplicity. The interactions are much simpler, and it can be done systematically. So that's what we are going to see in the rest of the lectures. Now, this idea is much more general than what I presented here so far. And it comes from a long history of research that goes back to, again, to Heisenberg with Euler in 1936. But I should maybe have included Bethe and Peierls in 1935 there. It sort of got developed in particle physics and condensed matter physics in the late 60s and 70s. And it was crystallized in what Weinberg called the Folck theorem. Folck theorem is a theorem that we don't know how to prove, but we also have no counter demonstration and no evidence that it's wrong. And this Folck theorem says, and I at the same time pay homage to Steven Weinberg, who died less than a year ago, a great man. And the Folck theorem says that the quantum field theory generated by the most general Lagrangian with some symmetries generates the most general S matrix that satisfy the principles that you want, namely obeys quantum mechanics, of course, because it's an S matrix, a Lorentz invariance, and unitarity, cluster decomposition, in those symmetries with no further dynamical content, no further physical content, and that's an important thing. So it's the most general S matrix with the physics you want in those symmetries, and it can be generated by quantum field theory with the most general Lagrangian. Now, quantum field theory with a Lagrangian you can transform to Hamiltonian, and normally particle physicists and nuclear physicists like to talk about the Lagrangian because it's easier to implement the symmetries at the Lagrangian level, but you can think of Hamiltonian as well. And that's exactly what I considered in the example before. I'm going to describe a non-relativistic quantum mechanics system with the most general potential that I can have, including 3 and more body forces. So, but this formulated this way, it can be applied much more generally. So you take this Lagrangian, you identify the degrees of freedom that you have in your problem. You write the most general Lagrangian. That means an infinite number of terms in the Lagrangian. So that's a departure to what many people have thought before, right? You were probably used to consider potential with one term or one type of interaction, not worry where it comes from. Here we have to include all of them. So these are called operators in quantum field theory. They will involve a field that corresponds to that particle, arbitrary powers of that field, arbitrary number of derivatives, so arbitrary powers of the field, arbitrary number of derivatives, that forms an operator. There's going to be a number in front. Then you use bidimensional analysis. It has to depend on the scales of the problem. So here I'm interested in as I said, any realistic case where the theory is valid up to a certain energy that I'm calling m high, and I'm interested in physics at a lower scale of momenta that I'm going to call m low. So there will be a power of this scales here, and then there will be parameters that are dimensionless that will depend on the underlying physics, the physics at high energies or small distances. And those are called low energy constants or Wilson coefficients, depending who you talk with. And then the big task of an effect field theorist is to relate this most general Lagrangian with the most general S matrix, so do this calculation. And in order to do that, since you have an infinite number of terms, it's crucial that you have a way to say this term will be this important to this observable, which is summarized in the S matrix, because the S matrix gives rise to all observables. So what you want is a systematic expansion for the S matrix. It's going to have essentially two components, something that comes from the dynamics that you can calculate. Meaning, in terms of quantum field theory, these are loops. You think in terms of loops. In terms of non-relativistic quantum mechanics is a solution of the Schrödinger equation with a given potential that you can calculate. And that's going to contribute some power on this, of the small parameter. And then if you know how to relate the two, which is called power counting, then you go to the next order, which contributes a higher power of the small parameter, and then you go to the next order, and so on and so forth, and it's systematic. At any given order, you are going to have an error, which corresponds to the order that you are not including, and then you are going to have terms that depend on what's called the regulator that makes all this integrals, the integrals that appear finite. You might have an infrared regulator, which you might want to put your system in a box for practical reasons. And those terms all have to be small, and that these terms introduced by these regulators are small is what's called, ensuring that that's the case is what's called renormalization. So that in the end, at a given order, you're making an error that's small, namely next order, and then you can go to next order and improve your calculation. This is a bit like what you do in QED, where you have a small coupling constant and you can consider different powers of this small coupling constant. But here I'm not relying on there being a small coupling constant. So I can deal with strong interactions in the same framework. The crucial element is power counting. The crucial ingredient for the power counting is renormalization. So there are these loops, these dynamical effects. They depend on the regulator, but then there are the parameters at the Lagrangian, which are called the Baire parameters, and we can use the Baire parameters to eliminate this dependence on the arbitrary regulator, and I'm going to give examples next. But at the end of the day, then what you have is the small scale of your small energy of your system in finite parameters, and then you have to estimate these finite parameters. And technically, what's done to estimate those is what the concept of naturalness that was formalized by 't Hooft and Veltman in the late 70s. And the idea is that if I know how the Baire parameter depends on the cutoff, then if that means that I know the sensitivity of the Baire parameter to high energy physics. If I therefore replace the regulator by the breakdown scale of the theory, I get an estimate of the size of the parameters. And we are going to see in a specific example soon, well, the case of the delta function interactions, how this naturalness is simply a statement of non-fine tuning. And non-fine tuning corresponds to a breakdown of this naturalness. So this idea has been applied in particle nuclear physics, condensed matter, in many different ways. And basically, you see the world as an onion, as a sequence of layers of effect field theories, and you see where you want to focus on your distance scales or your momenta scales, and for that there is an effect field theory. You just have to find construct that effect field theory for that scale. Whether that converges to some theory of everything or not is philosophical arguments in my opinion. But this is a framework for the emergence of theories at different scales that are all connected. In principle, one can relate one theory to another, but in many situations we can't not do that practically, and we just live happily with a effect field theory and do calculations within that effect field theory. So I'm, as usual, very late already. Lucas already gave me a sign that I still need 15 more minutes to finish what I wanted to do, and I don't have that time. So let me just tell you what I'm going to do next, namely tomorrow. So with this general idea of effect field theory, I'm going to implement it in a problem of the non-relativistic quantum mechanical system with a short-range interaction at the two-body level first. So I'm going to consider a system where I have only one particle, 1 degree of freedom, so one type of particle if you want, say a helium-4 atom. And I'm going to describe with a field that's given in terms of its annihilation operator. So I grew up with quantum fields, so I talk about quantum fields. I know that in condensed matter and atomic physics, people frequently go directly to the annihilation operators. It's just a question of doing some extra integrals. So that's going to be the degree of freedom. I'm going to call the mass of that particle m, which is then 2 times the reduced mass in the two-body system. And the only assumption I'm going to make about this mass is that it's much larger than the energy that I'm interested in. So the system is non-relativistic in other words. Then I impose symmetries, which are going to be the ones that you probably didn't even think about. It's Lorentz invariance, parity, time reversal, particle number is going to be conserved. So if I start with 2 particles, I end up 2 particles. It's not so when the system is relativistic. And then I write the most general Lagrangian for this system, which is going to have terms that depend on, that are only on the 2 fields, psi and psi dagger, or alternatively the annihilation and destruction operator, with a term that you might be familiar with. It's just a kinetic, the kinetic terms in a non-relativistic expansion. This is the grad square over 2m of the Schrödinger equation, right? And then I have the contact interactions written in field theory language, just a constant times 4 fields at the same point, which means a contact interaction, or 2 derivatives of a delta function, because that's 4 fields at the same point. I can have 3 fields coming together and then going out. So that's a 3-body force, which is just a contact 3-body force, contact 4-body force. I can consider more derivatives and so on. I'm not going to go into those details. I'm just going to state, which I think is believable, that this general framework of quantum field theory, then in this particular case that we are interested, reduces to non-relativistic quantum mechanics with those potentials, delta function potentials. And then what I was hoping to do still today, but it's going to be tomorrow, I'm going to go back to the 2-body system. I mean, I'm going to stick to the 2-body system and see how this is implemented without assuming a square well, without assuming a particular short-range potential. So my 2-body potential is going to be a contact interaction, a 2-derivative contact interaction, that's a delta function, a 2-derivative delta function, and so on. And I'm going to see how I implement this approach systematically. So I'm going to solve the Schrödinger equation for a delta function, which many of you might have seen before. If not, you're going to relearn it, or going to learn it. And then I go to the next leading, that's going to be the leading order. Then I'm going to go to the next leading order and see the effects of this interaction. So after I do that with the 2-body system, then I'm going to go, surprise, surprise, to the 3-body system, where there are going to be surprises there. And that is going to be the whole physics of FMOV, or more generally discrete scale invariance. Okay. I think for today, I think this is enough because I should leave some time for questions, and also we are running a bit late, right? So, okay.
Thank you, Bira. Do we have any questions?
Hi, Professor. My name is Pedro. Thank you for the great talk.
Thank you.
In the slide where you were talking about the deuterions and pions and you mentioned the scattering length, I didn't fully understood it, but my interpretation for the scattering length is that when you have it positive, you have an repulsive interaction, and you have negative scattering length, you have a attractive interaction. How that affect the topic? I don't fully understand.
Well, no, that's a good question because it's a bit counterintuitive. Normally, people indeed say negative scattering length is an attractive interaction. And that gives rise to, for example, if you neglect the effective range. So let's suppose you neglect all these terms here, effective range, shape parameter, and so on, and you still have this, and you still have that guy here. And if it's negative, you're going to see that you have a virtual state. Okay? So it's attractive. The particles want to be together, but it's an attraction that's not sufficient to have a bound state, at least not a shallow one, and one close to a low energy bound state. Okay, so then in that situation, if the scattering length is large and negative, this virtual state here is very close to the real axis. Okay, and it, as you said, it reflects attraction. The tricky part is the positive scattering length. The positive scattering length, it's either repulsion, namely no bound state, right, or it's a shallow bound state. It represents a shallow bound state. So if I increase the attraction, as I increase the attraction, this virtual state goes up, and at some point goes to the positive imaginary axis. In that case, again, assuming that it's close to the origin, so I can neglect all these other terms here, you are going to see that you have then a bound state with a binding momentum, which is 1 over A2. So in this case, I think you still have attraction. It's just that the attraction made a bound state, and then the scattering length flip sign. So the scattering length positive does not necessarily mean repulsion, but it might mean a shallow bound state which comes from attraction. Does that make sense?
Yeah. Okay, so another question is maybe a bit detoured.
Yeah, but then just very quickly, because you mentioned the pions and so on, because that provides an example, or helium-4 for that matter. So let me just go back to where am I? Here, for example. The positive scattering length for helium-4, for example, in large, means that there is a dimer, helium-4 dimer. There is a bound state of 2 helium-4. Potential must be attractive in order to get that, right? And the same thing is in the nuclear case. In this channel here, there is a bound state which is called the deuteron, the simplest non-trivial nucleus. In this channel here, where the scattering length is negative, there is attraction, but not enough to bind the two particles. So 2 neutrons, for example, are close to being bound, but are not.
An effect on this nucleus interaction. Do you expect to see like a peak of energy or anything like that? How do you see the effect that you talk about?
Which effect specifically? I mean, the existence of a shallow state.
Yeah. For example.
Either virtual state or a bound state, means that the phase shift has a particular behavior. So if I go back to those formulas, well, I don't have the formula explicitly here, but maybe you can imagine that you can get that from here. So this, if you compare this formula with this guy here, you see that what we have here is an expansion for k cotangent delta, okay, of the phase shift. So if you can neglect these terms, and if this term is very small, that implies that the phase shift is close to pi over 2. So if you work this in a little bit more detail, you see that when there is a virtual state, the phase shift grows very quickly, passes pi over 2, and then falls off. And when it's a shallow bound state, then it starts by convention, by what's called Levinson's theorem, starts at pi and then goes down and passes pi over 2 and goes down. So the phase shift with these conventions for the phase shifts are large at low energies with one of these two behaviors. For a resonance is more perhaps what you were, might be more intuitive. Then the phase shift is sort of slow moving, but then all of a sudden it goes very quickly. And then the reflections in the cross-section, that the cross-section has a huge bump close to the real energy of the resonance. The signal of these two guys is a bit less well known, but it's in a sense similar to the resonance.
No, yeah.
Does that make sense?
The resonance, yeah, but the bound state and virtual state, I can't imagine.
No. Yeah, so then as a homework, you look at, this is K cotangent delta, and you see what the shape of K cotangent delta is when you can consider these guys to be small. This to be small, for sure, you might see then what's called effective range approximation of the effective range expansion. And even simpler is to also consider this to be small and just consider this to be large. So it's just, let's say, 0. I mean, 1 over A is 0. The phase shift is pi over 2. So, but then different values you can play and see what the phase shift looks like. And the phase shift, well, phase shift is linked to the S matrix or to the T matrix, of course, and that's related to cross-section. So one next step is to look at what the cross-section looks, and you're going to see if you shoot 2 helium-4 atoms, what behavior the cross-section should have.
Okay,
Make sense?
So we are running a little bit late, but Bira is going to give 2 more lectures. So I ask if you have further questions, you can ask him during the lectures or during the coffee break.
Okay.
So let's take Bira again.
Okay, thank you.
Hello, Professor Nazarenko. Can you hear me?
Yes, I can hear you.
Okay. For the next lecture, we have the Professor Sergey Nazarenko. Thank you for accepting our invitation, Professor. Let me present him. Professor Nazarenko did his PhD at Landau Institute for Theoretical Physics at Moscow. He has a postdoc at the University of Arizona, and he has another postdoc at Rogers University at New Jersey. He has worked as professor and researcher at the University of Warwick and as researcher at Landau Institute. Currently, Professor Nazarenko is the research director at Institute of Physics of Nice in France. The focus of his research is fluid dynamics, wave turbulence, no equilibrium system, and ultra-cool gases. He has 2 books about these topics and many papers. So we can start now. So please, Professor.
Yes, I thank the organizers for a very kind invitation. I'm very happy to present at the school. So, okay, let me just start straight away. So I'll be talking about waves and vortices in turbulence of Bose-Einstein condensates. And so first of all, kind of overview, bird's eye view. So why can we even talk about turbulence in systems like Bose-Einstein condensates, and in fact, taking them broadly in nonlinear optics. Okay, so what's common between fluid dynamics, where turbulence is normally observed, and BEC systems and optical systems? Well, to answer this question shortly on very kind of hand-wavy level, you could think of the coherent systems like Bose-Einstein condensates are described by a so-called condensate wave function, which is a field. Okay, and light is also a field, it's an electromagnetic field, right? So this is instead of say particles like in usual classical mechanics, right? So then field is, you could instead of a point particle, you can think of as a cloud, all right, or some distribution of probability which can move in time, right? And it turns out that the properties of motion of such a probability cloud has a lot of similarity with fluids. And indeed, it was demonstrated a long time ago, about 100 years ago, by Madelung, who represented the usual well-known classical textbook Schrödinger equation for a single particle into a hydrodynamic form. And so, and then the fluid properties will become even more apparent when we deal with the coherent behavior of many particle systems that are described by so-called Gross-Pitevsky equation. And that will be the main model for my course. So this equation is written here. So this equation is for so-called condensate wave function, which is a scalar, complex scalar function. People consider such a field in various situations in three-dimensional, also there are some setups that do two-dimensional and even one-dimensional systems, right? And that is also as a nonlinear term. So difference with usual linear Schrödinger equation is that extra term, which is self-interaction of the system. And this interaction can be either repulsive or attractive, right? And that will depend on the sign of that coefficient, plus or minus y. So in nonlinear optics, such systems are called focusing, which stands for attracting in atomic physics, or defocusing, which is repulsive. And so the systems, I guess, described by Gross-Pitevsky go beyond the Bose-Einstein condensates, which of course the main application. This equation is used in nonlinear optic systems very widely, and even to describe cosmological evolution of early universe and dark matter somewhat. The signs, the focusing and defocusing. So in terms of Bose-Einstein condensates, the attractive potential is realized in rubidium gas or sodium, and I'm sorry, repulsive case. And the focusing case is realized in lithium, which makes condensates highly unstable in more than one dimension, which leads to sudden bursts and collapses. We'll be talking in this course too, today in fact. So further, we should mention that Gross-Pitevsky equation is often used for modeling superfluid turbulence in superfluids helium-4 and 3. So here, there's a qualitative model. Okay, it's not as well justified as for rarefied gases, but apparently it contains so many key features of superfluid quantum turbulence, such as quantized vorticity. That is also used in, for describing helium, superfluid helium at temperatures close to 0 as well. Okay, so, and of course, Gross-Perevsky equation in each particular system is modified by extra terms to describe retaining potential or dissipation or forcing terms or higher order nonlinear terms. So here in this audience, perhaps I shouldn't be explaining what Bose-Einstein condensate is, right? So it's actually, we say it was discovered recently, but it's actually been already 27 years ago. So that state was discovered. What was discovered, what was relatively recent is that turbulence studies in Bose-Einstein condensates realized. So it turned out to be a brilliant system to study turbulence and its potential. A future discovery is still waiting to be done in this particular field, turbulence in Bose-Einstein condensates. So some of which I will mention, but we'll discuss the future work in this area too. So now the second application I mentioned, nonlinear optics. So you see, in nonlinear optics, the effective time, the time coordinate is actually not really time, but it's a distance along the beam. So it's an effective time. And so this makes it impossible to realize three-dimensional turbulence, because the two other coordinates that are left are in transverse plane to the beam, and so therefore the 2 is the maximum dimension in this case. So in the Physics Institute of Nice, we have actually cold atoms group and optics groups that realize such experiments. So for example, this experiment in rubidium atom cell is experiment in a group of Robin Kaiser, and they've done some very nice work about what they call non-equilibrium precondensation. It involves some turbulent dynamics in such a cell. And another group I should mention that I've collaborated with sometime in the past, it's a group studying optical turbulence in liquid crystals. And here, in fact, it's the liquid crystal cell is in between of two thin planes, and therefore we bound yet another dimension, and effectively it becomes quasi one-dimensional system, and it exhibits very nice properties. So the third application I mentioned is early universe. And so here, in very, very early universe, actually what's written on this slide is starting from 10 to minus 12, but in fact much earlier than that. I mean, there was a sequence of phase transitions, okay, and which were accompanied by symmetry breaking. And the simplest model that can help us understand the symmetry breaking would be precisely the Gross-Perevsky model. So now I mentioned the fluid properties of such systems described by Gross-Perevsky equation, and that they come via Medellin transformation. So what's Medellin transformation? It's simply a representation of the complex scalar condensate wave function in terms of amplitude, positive amplitude, and the phase. So, and then if we do such a representation, it turns out that the equation written in terms of rho and phi takes a fluid form. So the first equation is just nothing but mass conservation. And in terms of quantum mechanics, it means you preserve total probability. And the second equation, if you define velocity as two gradients of phi, so you see the phi, 2 phi becomes a velocity potential, so that we have momentum conservation equation. And you see, so that on the left-hand side of this equation, we have the material time derivative of velocity field along the fluid path. And the first term in the second part is just the usual hydrodynamic pressure with a term, force, with a pressure proportional to rho squared, the density squared. So we have a fluid with adiabatic properties with adiabatic index equal to 2. But there is an extra term which is not present in classical Euler equations for fluid dynamics, and it's written here, and that's it's called the quantum pressure term, and it makes dramatic. It's very important and make the quantum system rather dissimilar in some respects from the classical fluid dynamics. So now, how to get these equations for that I just said, for in terms of the mass conservation. So essentially, so I have to say that I will mention some simple exercises, but I will also share with you via organizers, or maybe directly I can send a bigger file in which some more detailed derivations are given or exercises and solutions. But here I go through some simple exercise like that. How to derive the mass balance equation, continuity of mass equation. So what we do, we take equation, the Gross-Pitevsky equation, okay, and so multiply it by complex conjugate of psi and add to and subtract its complex conjugate, so that on the left-hand side, I have it will combine together by the product rule into derivative of density, which is mod psi squared, right? So then what's interesting that the nonlinear term during such a procedure, when I add the complex conjugate, will cancel. And so the nonlinear term doesn't give any contribution to that. That's why Magalung obtained the same equation just based on the linear Schrödinger equation. But what will be left is a term that arises from the Laplacian of psi, and we can represent it in this form, taking the divergence operator outside, okay? And then it's clear if you substitute psi in the form of amplitude phase representation in terms of rho and phi, then it's clear that we will get what we need. We get the term divergence of rho times u. So I will leave the okay. So I won't go through the second equation, although it's written here. But I leave it as for people who are interested to as an exercise for themselves. So let me just have a little bit more discussion of various terms, right? So as I mentioned, the first equation for density is a mass balance. It's exactly the same as for quantum fluids. So the momentum balance equation, it's very similar to the one in classical fluid. Okay, so with if we think of pressure as adiabatic pressure proportional to rho to power gamma, with gamma equal to 2, but we can also see, okay, so, but we can also see here that if S is equal to 1, which corresponds to attractive potential, pressure is actually negative, which never usually never happens in classical fluids unless you have oversaturated vapor. So then what is the consequence of that of negative pressure is actually precisely that the uniform state with rho equal to constant is in fact unstable. And we will consider that, that fact just in a few moments. So what will be important for us that the Gross-Pitevsky equation conserves two positive invariants. One of them is called mass, which is simply the integral of the density over the entire physical volume. And the second one is density, which is also Hamiltonian for the Gross-Pitevsky equation. But you see, the energy contains of two parts. The one that is the same as in linear Schrödinger equation, it's responsible for the linear dynamics. And the second one is interaction term. So yes, sometimes in terms of particles, one says it's free particle Hamiltonian, non-interacting particle, and the second is interaction term. And you see, again, interaction term can actually have negative, be negative if we have attracting fluids. And that has big consequences because the Hamiltonian sometimes can turn negative, and that will be related to the collapsing behavior. But also what will be important for us, that presence of such two invariants is similar to what we have in two-dimensional fluid dynamics. Namely, in two-dimensional fluid dynamics, as I will mention later, there is energy conservation, but there's also another quantity that's called entropy, which is a square of vorticity integrated space. And because of that, we will have similarities with two-dimensional turbulence, in particular, the dual cascade behavior, in particular, the fact that energy and these two invariants in the scale space cascade in the opposite directions. But this will be a little bit later. So this course is about waves and vortices in BSC turbulence, but okay, when talking about waves and vortices, it's impossible not to mention solitons as well. Okay, so they are actually, in this particular context, they are very, very close relatives to both vortices and waves, as you will see soon. So, what is condensate in this particular model? Well, the simplest state of condensate state is when we consider infinite system in physical space, and such that its density is independent of coordinate. It is represented by such a simple solution. You can simply plug that wave function with A0 being a constant, positive real constant. You can plug that into your Gross-Pitevsky equation and immediately see that this solves the equation. You see, so this is a solution is rotating, oscillating in the complex plane, right? With a frequency which is proportional to the square of the amplitude, which is density. Okay, so now in the extended nodes, so the ones of you who are interested can find study of stability of condensate. And what I'm saying to you, and you today you take it for granted, that in the attraction case, the condensate is unstable. This uniform state is never going to remain uniform if you introduce small perturbation to it. And in defocusing case, it's stable. So for today, you just believe me, but this you can see as an exercise in the extended notes that I will provide. But I will, but what I will consider is what this instability actually leads to. Okay, namely the collapses, and these collapses are extremely interesting from both physics and mathematics point of view, because this is creation of the finite time singularities in the system. Okay, so to consider such collapses, okay, so I'm referring to work, pioneering work of Vlasov, Petrichin, and Talanov. So they consider the system that kind of represents the width of the condensate distribution. So so you take the density multiplied by R squared. So it's mean R squared, if you wish, right? Mean R squared will be this quantity A divided by the total mass. Okay, so a mean square radius of your condensate cloud. So these people obtain in 2 dimensions exact relation for this quantity A. Okay, namely that the second derivative with respect to time of A is equal to 8 Hamiltonians, 8 energies. But this is a very rare success when you obtain something exact like this for nonlinear models. So, but now that you have this relation, you can integrate it twice, right? Because it's h is a constant, so you just simply integrate it twice. You get 2 integration constants, C1 and C2, let's call them, right? And then in fact, okay, maybe perhaps I should mention that this fact that you can do this kind of, find this kind of solution is related to symmetry. Perhaps many of you know that symmetries are related to some conservation laws, right? And in this particular situation, the corresponding symmetry is related to the scale transformation, which is called length transformation. But okay, so this is just a remark that I leave without further explaining. But now what's clear that the quantity A can turn into 0, right? In finite time, if H is negative, right? Okay, so you see, originally the quantity A is defined as a positive quantity, right? Okay, but it's positive provided that the cloud, the condensate cloud, has some nice smooth properties. But if the cloud turns into just one point, A will be 0. And in order for H to be 0, it can't become 0 if H is negative, right? Then in this case, this term will lead to decrease of initially positive, and T squared at large T will always dominate over T or constant term. So it will inevitably become 0. And this is precisely the Vlasov-Petryshev-Talanov criterion for the collapse. So it says that in situations where H is negative, which happens when nonlinearity is strong, when psi has a great value, so that in your energy, interaction energy is bigger than the free energy. So you will have a collapse in 2D case. So then it was this criterion was in fact extended for three-dimensional situation in a paper by Zakharov, who instead of the exact equality obtained inequality of this kind. Okay, so this is exact equality that Zakharov obtained, but you see from this equality follows this inequality, because the second term here is strictly negative. And so in this case, it's clear for the same argument that if H is less than 0, it is a sufficient condition for collapse in 3D. So solution, if we have strong enough initial condition, solution inevitably ceases to exist in finite time with singularity, with infinite density shrinking into a single point. Right. Okay. So this was the rather violent and strongly nonlinear phenomenon of collapse that I just talked about. But now let's talk about the opposite extreme, where the waves are linear, so that the free Hamiltonian dominates over the interaction Hamiltonian. There are actually several kinds of waves that exist in BSC. Okay, so first of them is the simplest. It's simply matter waves or de Broglie waves. So these waves, when nonlinear term, interaction term in Gross-Piotrowski equation is much smaller than the linear term, okay, we can neglect it, and we will simply get back to the linear Schrödinger equation, for which we know the textbook solution, wave solution, right? Matter waves, okay, for psi function. And so you see that the frequency of such waves will depend to wave vector as wave vector squared. And you can think of it as a classical relation between energy and momentum, of classical meaning non-relativistic relation between energy and momentum for particles. So the second type of waves is actually when a strong condensate component is presence in the system, and then we have deviation not around the vacuum state, but around the constant coherent condensate state, and require that this perturbation is much smaller than the condensate amplitude. And then if we substitute such things into the Gross-Piotrowski equation, or we could even substitute them into the, well, in fact, into the fluid equations obtained by Madelung transformation, we just plug in these perturbations in the form of a plane wave. And so then okay, so the continuity equation will give us this, the mass continuity equation, right? Remember, when we deal with plane wave, then time derivative amounts in algebraic multiplication by frequency and space derivative amounts in algebraic multiplication by wave vector. So that's why this time derivative of rho term gives us this frequency multiplied by rho. And the second term, which is both Laplacian of psi, will give us k squared coefficient. And respectively, the second equation, the momentum equation, will give you the second equation complementing and making it a full system that we call the solvability condition, for which gives us a relation between frequency and wave number, and which is the famous Bogolubov dispersion relation. And so these are the Bogolubov waves in background of a condensate. So you can see that they are become similar to acoustic waves if we consider a small k limit, so that k to the power 4 can be neglected. So we can then see that omega is proportional to modulus of k, just like for sound waves. And in the opposite limit, when k is much bigger, or k squared much bigger than a condensate density, we can neglect this term and we go back to the previous example of the matter waves. And so we will, the other term, there's also another type of waves on background or propagating on vortex filaments, but this we will leave the consideration of these waves until we introduce vortices. So that was linear waves. What about the nonlinear waves? All right. So, and the solitons gives us the most famous example of the nonlinear waves. So it's just a single pulse propagating in space with particular velocity. So by direct substitution, for simplicity, we'll here consider one-dimensional case. And you can plug that in as an exercise by direct substitution, this expression, and do all the differentiations and see that the equation is satisfied. So you see what you see in this equation, that you see that dependence on x comes via x minus ct, which means that the waves propagate in x direction with velocity c. Okay, and so the other parameter, so c is a free parameter here, and another parameter is mu. That affects the amplitude. So these solitons are two parametric solution the solitons. But perhaps maybe it's not so satisfactory for me to say to you just go back and check by plug it into the equations. So let's just consider a simple case that we can treat very quickly here. Situation where velocity of propagation is 0. So in this case, let's consider psi just in the following form. Okay, let's consider some mu, some constant mu, and f just being a real function. Okay, so if we substitute it in the one-dimensional Gross-Pedevsky equation, time derivative term will give us minus mu f. Okay, when we cancel I, obviously. So this is a derivative term and the nonlinear term, right? So you can see, you can rewrite it by putting a second derivative of f on the left-hand side and the rest on the right-hand side. And you can represent the right-hand side as a derivative with respect to f of a certain expression. But then you can see that this equation is formally the same as a Newton equation for the for just a point mass moving in potential, so where x plays role of time and f plays role of position of that point mass. And you see, so on the right hand side we have a potential force. We have derivative with respect to position, which is f in our case, of some function that depends on the position. So it's a potential. So, and we know what happens with point particles moving in a potential field. So here's this function drawn, this potential. You see, it has two minima, right? And we know that what happens to when we put particle bounded by potential. So the particle, since there is no, this potential has infinite poles, so it will start bouncing from one side to another, and that will be a periodic motion. Okay, and there's only one situation where if we put particle right here in this unstable equilibrium. So this is so-called homoclinic trajectory. This, because it's at equilibrium, it will take infinite time to move in F. But remember, F is is our coordinate of the particle, right? And time is actually X. So in X, we'll have just one oscillation corresponding to such homoclinic trajectory. So if I integrate this equation over here, I have classical conservation of energy equation, right? If I multiply this equation by derivative of f with respect to x and integrate, right? So I can integrate both sides and I have energy conservation. So the first term represents the kinetic energy and the second is potential energy as usual, right? So this trajectory that I mentioned to you that passes through this local maximum corresponds to E equal to 0. So precisely that. And then I can plug E equal to 0 here, and I can separate variables. In this equation, I can solve it exactly. Just take this term on the right-hand side, take a square root of it, and integrate with respect to, and so, yes, and so integrate it, right? And I will have the following expression, okay? And so when I do that, right? So in fact, it's a table integral on the left-hand side. I can, can easily find. So by making substitution, introducing new variable z like this, then this left-hand side transforms into something that we know, which is just table integral Arcosh, hyperbolic cosine function. Okay, and so if you plug it back into terms of f, I get the following expression for f, and this is precisely the soliton, what we had, that particular case of soliton expression that I already gave you, but with velocity equal to 0. So this is this soliton, and it looks like this. So if here I fix parameter mu equal to 1 and consider different velocities, right? And so I see that the bigger the velocity is, right, the actually smaller the amplitude of the soliton. Small solitons propagate with velocities that are faster than big solitons. And in fact, if you consider very small amplitude solitons, they will propagate just like linear sound waves with the speed of sound. Okay, then that was for focusing nonlinearity. For defocusing nonlinearity, equally I can find a solution. In fact, one-dimensional Gross-Petersky equation is well-known integrable system. We can find even general solution in terms of the inverse scattering problem, and not just special cases as solitons that I'm giving you. So what's interesting in the focusing case? So you see what in focusing case, you see in the center of soliton, we had a density bigger than at infinity. And in defocusing case, density is actually smaller than at infinity. So it's called gray soliton, which turns in completely dark soliton at some point when when propagation speed is equal to 0, right? It can actually just hit the zero density, which in terms of optical systems, it would mean it will be completely black at this point. And these points where when psi becomes exactly 0 are very important. They are called phase defects because remember Madelung transformation, if density is 0, phase is undefined. In this particular example of one-dimensional system, in fact, the phase experiences a jump. If I pass through this point from the left to the right, it experiences jump pi. Okay, so just jumping ahead, I will mention to you that in multidimensional systems, such phase defects corresponds to vortices. Okay, in particular, and the jump will be not pi, but will be 2 pi when I go around such an object. So, and this jump is actually the circulation of quantized, and so because it can only take multiples of 2 pi, that's why it's called quantized vortices, and that makes a crucial difference with the classical fluid dynamics. So now I'll show you actually a cartoon that explains in very simple terms that that the solitons, one-dimensional solitons, are unstable via so-called snake instability. And here I take this is actually a book on plasma physics, collective phenomena in plasmas, by Boris Kadamtsev. But it considers such things as instability of solitons. And you can just see from the cover of his book how it works. Okay, so suppose you have a one-dimensional soliton, right? Now it propagates to the right. Okay, so and now let's introduce a perturbation of it. And in such a case that the amplitude of it is slightly bigger in the center than on the sides, right? And remember, I told you that the bigger solitons propagate slower than the weaker ones. And so this means that during propagation, the soliton will deform its form, shape, and it will become kind of like a snake, gets snaky, okay? But you see, but then the wavefront, the solitons, then this curved part of solitons will start propagating toward the center rather than strictly to the right. And because they propagate toward the center, they make density even bigger. They focus the density. So the density was bigger here, and it becomes even bigger. And so this means that this process will self-accelerate, you know, and will eventually break this soliton. Okay, so now one thing I should mention, that what is the result of this instability, that eventually one ends up with fully two-dimensional structures, and that also considered very important in dynamics of BSC condensate and nonlinear optics. They call John Roberts solitons, two-dimensional solitons. This would take a long time for me to actually go over them, you know, so how they look. But what's important for John Roberts solitons, such two-dimensional soliton, that it can also touch zero. If it is strong enough, like one-dimensional soliton, it can hit the bottom, and the density becomes precisely zero. And when it happens, then two-dimensional vortices appear in the system. It will be phase defects taking form of two-dimensional quantized vortices. Okay, so this means that if we have a one-dimensional soliton, so as a result of its instability, we can get a system of vortices. So vortices appear out of nowhere. So they get created by the nonlinear dynamics. Okay, so now let me actually consider vortices. And let's first of all remind ourselves what are vortices in classical fluids, right? So if let's consider some fluid flow with velocity field u, and let's consider a contour in space that embrace okay, so which is closed contour, and consider contour integral of velocity along this contour, right? Like in this sketch, right? dl being an infinitesimal small vector along the such a contour. So we know by Stokes' theorem in vector analysis that this integral can be represented as a surface integral of the quantity of curl of velocity, right? And this is integral is to be taken along the surface, which is spanned on this contour. Let's suppose you have a rubber sheet, you stretch it on this contour and take integral. So you transform contour integral into the surface integral. And the quantity that is here, curl of velocity, is called vorticity. That plays important role too in classical fluid dynamics. So, and then the classical result in the textbook fluid dynamics is a Kelvin circulation theory. It says if in an ideal fluid flow, which means I don't have any dissipation or some other non-ideal effects. So if I have extra forces, which are even forces can be present, but if they take potential form, so just as a gradient of something, then such an integral, a circulation integral that we defined, is not changing in time, provided that contour C is moving with a fluid, right? You kind of dye your fluid particles where the contour is originally, and these particles moved, and they mark a position of the contour at further moments of time. Now, as we know from classical fluid dynamics, viscosity, viscous dissipation breaks conservation of circulation, breaks conservation, the Kelvin circulation theory. Okay, and viscosity leads to dissipation of energy. What's interesting, so that quantum pressure term that that is present in quantum fluid equations, okay, also breaks the conservation of circulation, but with a big difference that quantum pressure term does not dissipate energy. So we can break conservation of circulation without dissipating energy. And what happens when you break it? In both systems, for classical viscous or quantum with pressure with quantum pressure, we can see it as a result of a reconnection of the vortex line. Okay, so which I will consider, but first let's introduce the quantum vortices. Okay, so the quantum vortices, okay, remember that velocity field in quantum case is defined by two gradient of phase of the condensate wave function, right? But then let's consider this circulation integral that we just defined and plug in that definition of velocity in terms of potential. And you see that we, since we're integrating derivative, what we do as a result, we obtain that it will be a change in phase once we go once around the contour. Okay, so you see what's important to understand that such change is not necessarily zero, because the even though the psi function is unique function of coordinate and time, the phase is not necessarily so. But because the psi must be actually the return to the same position, the psi function itself, then this means that if phase, remember it's entering in the exponent as e to I phi, right? When I substitute that into e to I phi, I must get zero result. What does it mean? It means that the phase should rotate in the multiple values of 4 pi, positive or negative. So usually okay, so in this situation, when this happens, is called vortex with charge n, plus or minus n, okay, positive or negative. So, but usually the states with n greater or equal than 2 are unstable. So the single charge vortices are much more typical, structurally stable, and more fundamental in the quantum fluid dynamics. And another thing what's important to notice is that in fact, this integral, right? So if we had phi defined everywhere in space, then it would have to be 0. It would be single valued function. But you see, when psi turns into exactly 0, we have a domain which is not simply connected. And so when this contour embraces the point where psi is 0, that's precisely the vortex circulation is encountered. So, and in fact, you can shrink that contour up to it embraces very tightly the position of psi equal to 0. And so, therefore, the geometrical location of vortices is precisely where psi is equal to 0, the function. So, what is the simplest vortex solution? We can obtain it if we substitute use polar coordinates and seek for the phase in the form kind of go into rotating frame of the supposed phase has a simple form of this polar angle in physical space minus time. So phase is rotating with unit velocity. So it looks like this, the phase. So obviously it will have a jump, 2 pi jump when we rotate once, right? Okay. When we substitute that, okay, and substitute psi function in this form, then for the amplitude, which we assume only function of the radius, distance from the coordinate origin, we obtain the following equation, right? So we instead of partial differential equation, which was initial Rospetevsky equation, we get the ordinary differential equation for function for the amplitude r. But this ordinary differential equation is nonlinear, and it turns out it doesn't have a simple analytical solution. But nonlinear second-order differential equations, everybody knows who can use MATLAB or something else how to solve such equations. And what we get as a result is something like that. So the shape of this function r is like this. And remember, in terms of density, r is a square root of density. So this is density of the vortex that we get. So you see that at very far away, at large distances, density tends to 1, right? It tends to constant. And at 0, it's precisely 0. So remember what I told you, that vortex is at 0. Okay. Then with the way we define the phase, it's obvious that the phase experience 2 pi jump, right? So therefore, the circulation is precisely equal to 4 pi, as we said, single charge vortex, right? What's also important to see that the density goes from 0 to constant value over some characteristic distance, right? They say that density heals itself, so to the one of the background condensate, and therefore it's called Hélène length, right? In fact, instead of a solution that I considered with such density at infinity equal to 1, as shown here, I could have rescaled my solution and consider arbitrary density and show that these characteristics, the distance at which we have Hélène length is equal to, is of order of 1 over rho 0. Right, okay, so perhaps I should just stop my presentation here to let you, because I think I'm pretty much 1 minute before my time is up. So you can ask questions if you have.
Okay, we have time for question. Please, Professor.
Oh, hello, Nazarenko. Nice to see you.
Hi, Vanille. How are you?
Fine. My question is, you place it in the very beginning that solitons, vortex, and waves are the interesting excitations to go to turbulence somehow. Or
yes.
Anyway, those are excitations that we are able to extract from the Gross-Pitaevsky. I know though that vortices interact with vortices. How does solitons interact with vortices?
Okay, so one example I already gave today, that soliton can create vortex due to its instability, right? So they can just appear, soliton can break and create vortices. That's one interaction, right? Okay, another type of interaction that you can have it other way around. So you can have 2 vortices, say with positive and negative charge, and they will be propagating like a vortex dipole, but they will interact with a background, let's say turbulent background, maybe with waves, or maybe some other distant vortices, and they can lose their energy. And so the distance between them becomes smaller and smaller and smaller until they shrink and annihilate. In fact, I will consider in my next lecture some simplest example of such vortex annihilation as well. Okay.
More questions?
So you could say, roughly speaking, that the solitons, they can also be 3-dimensional solitons, right? So that the solitons are just emergent vortices. So if you take soliton strong enough, it will contain vortices. And if you take soliton weak, sufficiently weak, it will turn into acoustic waves. So soliton is in between. In fact, the John Roberts soliton solution, okay, so it's a one parametric solution that if you take it strong enough amplitude so that it crosses 0, it will contain a vortex pair. and whereas in a very weak case, it will be just some weak acoustic pulse.
More question? There is a question here in the YouTube chat from Diego Hernandez. He said, does sound interact with the single vortices?
Yes, sound interact with, sorry, could you, does sound interact with vortices? Is that the question?
Yes.
Yes, yes, of course sound interacts with vortices, yes. And so in particular, so suppose you have some random sound waves in the system, and when vortices propagate in such waves, okay, so they can excite more sound, they can lose their energy and momentum into sound component, or they can suck it from the sound and become stronger. That depends on the particular vortex configuration, so that they can exchange, vortices can exchange energy and momentum with sound waves. And even if you initially start with only vortices and no sound, and let's suppose you have only two vortices of the same charge, right? Say plus 4 pi and plus 4 pi. They will start rotating around each other. And by rotating, they will emit sound waves. So sound waves will be radiating, just like perhaps what you saw in this cartoon of gravitational waves created by two rotating black holes. So you imagine your black holes are vortices, and sound gravitational waves radiated from it, right?
Okay, now he's asking about how this picture changes with the dimension of the system.
Okay, so in 2 dimensions, the vortices take form of just points, so with positive or negative circulation. So in 3-dimensional system, and that actually will be in the beginning of my lecture tomorrow, the vortices are concentrated on the on so-called vortex lines, right? So there's the curves, 1-dimensional curves in 3-dimensional space, and these lines will move, and they can actually collide with each other. And when they collide, they will emit sound. Okay, so when they collide, they will reconnect. They will change the topology configuration, and the excess energy will be radiated as waves. So whereas in 2D, so 3D is obviously a more complicated picture. So let's say if you have many vortices like that, and that's what we call vortex tangle. So suppose you have just the whole pot of spaghettis with these quantized vortices moving, and this is in the essence what people think of as strong superfluid turbulence. So this motion of a vortex tangle. And this vortex tangle will have acoustic waves in between of them. So the essential component interacting with the vortex tangle. So in 2 dimensions, instead of this vortex tangle, you will have a gas of this point-like vortex atoms moving around, which will also be colliding. Sometimes during the collision, plus and minus vortex can annihilate and create sound. So obviously will be no reconnection as such, but it could be annihilation process. So that also coming actually in the beginning of tomorrow's lecture.
Okay, we had one more question in the chat. As you mentioned, circulation is not conserved in Gross-Pitagoric equation. What about the helicity?
And helicity is also not conserved. So the situation with helicity is even worse because it's kind of non-local invariant. So, but in fact, some interesting things happen with helicity when you go to specific configurations. So that it might be kind of quasi-conserved for a while and for some interesting states. But it's, yes. Sorry, I would not want to go to explain about helicity because it's a little bit more involved. So that.
Okay, more question? If there is no more question, let's thank Professor Nazarenko again.
Thank you.
Thank you, Professor. See you tomorrow.
See you. Thank you.